Alright, here's a classic LeetCode problem. Find the total number of continuous subarrays that sum to k. Now, the brute force way is to check every possible subarray, which is O of n squared. But here's the genius trick: we use prefix sums combined with a hash map. At every position, we ask, hey, have I seen a previous prefix sum that, if I subtract it from my current prefix sum, gives me exactly k? If yes, boom, that's a valid subarray. First things first, we create a hash map called prefix map. This thing is gonna store every prefix sum we've encountered and how many times we've seen it. And here's a subtle but critical detail: we seed it with 0 mapped to 1. Why? Because if our running sum ever equals k exactly, we need to count that as a valid subarray from the very beginning. Without this initialization, we'd miss those cases entirely. Super simple here, we set up prefix sum starting at 0, which will accumulate as we walk through the array. And count starts at 0 too, which is our final answer tracker. Every time we find a valid subarray, we'll bump this count up. These two variables are doing all the heavy lifting together. Now we enter the loop, and this is where the magic happens. For each element, we add it to our running prefix sum. Think of prefix sum as the total of everything from index 0 up to the current index. It's like a running total on a receipt. At any point, you know exactly how much you've spent so far. And this is the key insight of the entire algorithm. We compute needed, which is prefix sum minus k. Here's the intuition: if there's some earlier prefix sum that equals this needed value, then the subarray between that earlier point and our current position sums to exactly k. It's like saying, if I've accumulated 10 total and I need subarrays summing to 3, I'm looking for a previous point where the total was 7. 10 minus 7 equals 3, that's our subarray. Watch what happens here: we check if needed exists in our prefix map. If it does, we don't just add 1 to count, we add the entire value stored in the map. Why? Because that value tells us how many times we've seen that prefix sum before. Each occurrence represents a different starting point for a valid subarray ending at our current index. Multiple matches means multiple valid subarrays. After we've checked for valid subarrays, we record our current prefix sum in the map. We either increment its count if we've seen it before, or set it to 1 if it's new. Here's the thing: the order matters. We record after checking, not before. If we recorded first, we might accidentally count the current index as its own previous prefix sum, which would mess everything up. Finally, we return count, the total number of subarrays that sum to k. In our example with array 1 2 3 and k equals 3, we'd find 2 valid subarrays, the subarray containing just 3, and the subarray 1 plus 2. The debug logs throughout help you trace exactly how the prefix map builds up step by step. So what's our complexity? Time is O of n, one single pass through the array. Space is O of n for the hash map storing prefix sums. We went from an O of n squared brute force to linear time, which is beautiful. Here's your takeaway: whenever you see subarray sum equals something, think prefix sums plus a hash map. It's one of those patterns that shows up everywhere once you know it.